Every clock you have ever trusted was built on an assumption so deep it became invisible, the assumption that time has always existed, that somewhere behind the ticking, behind the counting, behind the steady drift from one second to the next, time simply continues backward without limit. But here is a strange and quiet truth that has been gathering force in the last few decades of physics. Most working cosmologists no longer believe the Big Bang was the beginning of time, not privately, not reluctantly, openly, in published papers and professional surveys. The old certainty of a universe born from an infinite singularity, a hard wall of creation beyond which nothing existed, has been dissolving under the weight of new mathematics and new observations, replaced by something far more interesting and far less tidy. Tonight, we are going to follow that idea, gently, without rush. We are going to trace the question backward, past the first atoms, past the first light, past even the first conceivable fraction of a second, to a place where time itself begins to thin and blur, where physicists have built real, testable models of what might have existed before the very concept of before had any meaning. If this kind of exploration appeals to you, if you enjoy falling asleep to ideas that are vast and unhurried, you are welcome here. Consider subscribing so these journeys continue finding you. Now let the ordinary world grow quiet. Let the room around you become the edge of something much older and much stranger. We begin at the wall, and then we ask what lies on the other side. Close your eyes and picture what most people imagine when they hear the words Big Bang. An explosion. A blinding flash in the darkness, something bursting outward from a single point into the emptiness of space, like a firework going off in a vast, pre-existing room. It is one of the most persistent images in popular science, and almost every detail of it is wrong. There was no room. There was no darkness waiting to be filled. There was no outside vantage point from which to watch something explode. The Big Bang was not a detonation in space. It was the rapid expansion of space itself, of the very fabric in which distance and direction have meaning. And this distinction, though it sounds like a technicality, changes everything about the question we are exploring tonight. What physicists call the hot Big Bang is really a description of a state, an extremely hot, extremely dense condition from which the universe has been cooling and expanding ever since. Think of it less as an event with a fuse and more as a condition with consequences. The evidence for this thermal beginning is overwhelming. The way galaxies are distributed across the sky, the precise abundances of hydrogen and helium and lithium forged in those early minutes, the faint glow of microwave radiation still arriving from every direction, all of it points to a universe that was once incomprehensibly hot and has been stretching and cooling for roughly 13.8 billion years. But here is where the story takes its first quiet turn. In the 1960s, Roger Penrose and Stephen Hawking proved a series of elegant theorems showing that if you trace the expansion of the universe backward using general relativity, Einstein's description of gravity as the curvature of space-time, you inevitably arrive at a point of infinite density, infinite curvature, infinite temperature, a singularity, a place where the mathematics collapses into nonsense and the laws of physics, as we understand them, simply cease to operate. For decades, this singularity was taken as the beginning, the wall behind which nothing could be said, the edge of the map where physicists wrote, in effect, "Here be dragons," and no further questions. But those theorems carried assumptions about the nature of gravity, about the behavior of matter under extreme compression, about the smooth continuity of space-time at the smallest scales, and one by one, over the past 40 years, those assumptions have started to crack. The story of what existed before time is, in a very real sense, the story of what happens when we stop trusting the singularity. There is a number in physics that functions almost like a locked door. It is unfathomably small, 5.39 times 10 to the negative 44 seconds. This is the Planck time, and it represents the earliest moment after the origin at which our current theories can say anything coherent at all. Before this instant, if before even applies, lies the Planck epoch, a realm where the known laws of physics dissolve into something we do not yet have the language to describe. To understand why, it helps to think about what was happening to the universe at that scale. At the Planck time, the observable universe was compressed into a region smaller than the Planck length, roughly 1.6 times 10 to the negative 33 centimeters. For perspective, this is to an atom what an atom is to the entire observable universe, and at that scale, something deeply unsettling occurs. The gravitational field becomes so warped, so turbulent with its own quantum fluctuations, that the distinction between space and time loses its ordinary meaning. Space-time itself becomes a kind of quantum foam, a roiling, uncertain fabric where geometry is no longer fixed and direction has no stable definition. Imagine trying to measure something with a ruler that is itself vibrating so violently it cannot hold its shape. That is the situation physics faces at the Planck scale. Any attempt to probe this regime would require energies so extreme, around 10 to the 19th billion electron volts, that the act of observation would create tiny quantum black holes, destroying the very information you were trying to gather. It is as if the universe has built a veil into its own structure, a resolution limit below which no instrument, however clever, can render a clear image. This is not merely a practical limitation, it is a theoretical one. General relativity, which describes gravity beautifully on large scales, needs smooth, continuous spacetime to function. Quantum mechanics, which governs the behavior of particles, requires a fixed background against which events unfold. At the Planck scale, both frameworks demand things the other cannot provide. Gravity becomes quantum, quantum effects become gravitational, and neither theory alone can handle the merger. This is why physicists speak of the need for a theory of quantum gravity, a framework that unifies these two pillars of modern physics into a single coherent language. We do not yet possess such a theory in its complete form, but several candidates exist: loop quantum gravity, string theory, causal set theory, and each of them in its own way has something remarkable to say about what lies behind the Planck curtain. The curtain is not a wall, it is a limitation of our current vocabulary, and the effort to develop a new vocabulary, one adequate to describe the conditions at the very origin, is one of the deepest and most beautiful projects in all of science. It is worth pausing here to consider something that often gets lost in popular accounts of the Big Bang. The singularity, that point of infinite density and zero volume at the supposed beginning of everything, was never observed. No telescope has seen it, no instrument has measured it, no experiment has confirmed its existence. It is, and has always been, a prediction, a consequence of running the equations of general relativity backward in time until they produce a number that is no longer meaningful. And that is a very different thing from evidence. When a theory predicts something infinite, infinite temperature, infinite curvature, infinite density, physicists do not usually interpret that as a description of reality. They interpret it as a signal that the theory has been pushed beyond its domain of validity, a sign that something is missing, a confession, really, that the mathematics is trying to describe a situation for which it was not designed. General relativity is a remarkably successful theory. It describes the orbits of planets, the bending of light around galaxies, the rippling of gravitational waves across the cosmos, but it was designed for situations where spacetime is smooth and classical, where the curvature is finite, the densities are manageable, and quantum effects can be safely ignored. At the center of a black hole, or at the origin of the universe, those conditions are catastrophically violated, and the singularity that appears in the mathematics is not a triumphant discovery. It is a white flag. There is a second reason the singularity has lost its grip on cosmological thinking, and it comes from observation rather than theory. In 1998, two independent teams of astronomers made a discovery that reshaped our understanding of gravity itself. By measuring the brightness of distant supernovae, exploding stars used as cosmic distance markers, they found that the expansion of the universe is not slowing down, as everyone expected. It is accelerating. Some energy woven into the fabric of space itself, is pushing the universe apart with increasing speed. This force was named dark energy, and its implications for the singularity theorems are profound. Those theorems, proved by Penrose and Hawking in the 60s and 70s, rested on a key assumption: that gravity is always attractive, that matter and energy always pull things together. The discovery of dark energy, a repulsive component of gravity, directly undermined that assumption. If gravity can push as well as pull, the mathematical road backward in time does not necessarily lead to a point of infinite compression. It might lead somewhere else entirely, and so the singularity, once treated as the hard floor beneath all of cosmology, began to feel less like bedrock and more like a placeholder, a temporary answer to a question that physicists were only beginning to ask properly. Here is something that most people have never been told, and it changes the entire shape of the conversation. When cosmologists use the phrase Big Bang, they are quietly referring to two very different things, and only one of them is supported by strong evidence. The first is the hot Big Bang. This is the well-established observation that the universe was once in an extremely hot, extremely dense state, and has been expanding and cooling ever since. Every major piece of cosmological evidence, the cosmic microwave background, the distribution of galaxies, the chemical composition of the oldest stars, points to this thermal beginning with overwhelming consistency. The hot Big Bang is not a theory, it is a fact as firmly established as any in the physical sciences. The second is the Big Bang singularity. This is the theoretical extrapolation, using general relativity alone, of that hot, dense state all the way back to a point of zero volume and infinite density, a moment that would represent the absolute origin of time and space. And this is the idea that has been steadily losing credibility. The distinction matters enormously for the question at hand, because once you separate the two, once you recognize that the thermal state we call the hot Big Bang does not require an infinite singularity behind it, a door opens, a very large door. The question what came before the Big Bang no longer means what came before the beginning of everything. It means something much more tractable. What preceded the hot, dense, expanding state that gave rise to atoms, stars, and galaxies? And the most widely accepted answer to that question, at least among working cosmologists today, is inflation. Cosmic inflation is a period of extraordinarily rapid expansion that is thought to have occurred in the very early universe. During inflation, space expanded exponentially, doubling in size over 50 times in a sliver of time between 10 to the negative 36 and 10 to the negative 34 seconds. This expansion was driven not by matter or radiation, but by a field, the inflaton field, whose energy was stored in the vacuum of space itself. When inflation ended, the energy stored in that field was released and converted into a flood of particles and radiation, an event that cosmologists call reheating, and that moment of reheating is, in fact, what we mean by the hot Big Bang. The thermal cosmos we observe began not at a singularity, but at the end of inflation. This means that inflation itself, that period of exponential expansion, already occupies the space before the Big Bang, if we use the hot Big Bang definition. The before is not metaphysical, it is not speculative in the wild sense. It is part of the standard model of cosmology, taught in graduate textbooks and supported by decades of data. Physicists have already answered part of the question, what existed before the Big Bang? At least one layer of answer is an inflating universe, stretching and preparing the stage for everything that followed. To appreciate what inflation actually did, it helps to set aside the familiar and think about the universe as a fabric, not a fabric with things sitting on it, but a fabric that is itself everything, every distance, every direction, every spatial relationship between objects. And during inflation, that fabric was being stretched at a rate almost beyond description. In the span between 10 to the negative 36 and 10 to the negative 34 seconds, a period so brief that no human analogy can honestly capture it, the universe doubled in size more than 50 times, each doubling compounded on the one before. After one doubling, a region the size of a proton would expand to the size of 2 protons. After 10 doublings, it would be 1,000 times larger. After 50, it would be larger than the entire observable universe today. And this was happening everywhere, all at once, driven by the energy of a quantum field that permeated the vacuum of space. But inflation did more than stretch. It cooled. As space expanded, The energy density of the inflaton field remained roughly constant. It was a property of the vacuum, not of matter, but the temperature of any pre-existing particles or radiation dropped precipitously. By the end of inflation, the universe was almost perfectly cold, nearly empty, a vast, smooth expanse of space with almost no thermal content at all, and then inflation ended. The inflaton field decayed, releasing its stored energy in a process called reheating. Particles were born, radiation flooded the newly expanded space. The temperature soared to trillions upon trillions of degrees, and this sudden thermal ignition, is the event we have been calling the Big Bang all along. The reframing is quiet but revolutionary. It means the Big Bang was not the beginning. It was a transition, a phase change, like ice melting into water, except the ice was a cold, inflating vacuum, and the water was the scalding plasma of the early thermal universe. And just as you can reasonably ask what the ice was doing before it melted, you can reasonably ask what the universe was doing before inflation ended. This is not philosophy. It is not speculation dressed in scientific language. It is the direct, logical consequence of a model that has been tested against decades of observational data and passed every test. The cosmic microwave background, that ancient light released 380,000 years after the hot Big Bang, carries patterns that match the predictions of inflation with extraordinary precision. The slight variations in temperature across the sky, the statistical properties of those variations, the way they correlate on different angular scales, all of it aligns with what inflationary models predict. Before the Big Bang, there was inflation, and before inflation, that is where the deeper questions begin. That is where the Planck curtain hangs. And that is where the most daring ideas in modern physics are quietly waiting. One of the most remarkable things about the question what existed before the Big Bang is that it has moved, within living memory, from the realm of unanswerable philosophy to the realm of observational science. And the bridge between those two realms is made of light, ancient, faint, and astonishingly precise. The cosmic microwave background, or CMB, is often described as the afterglow of the Big Bang. It is radiation released roughly 380,000 years after the hot Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time. Those photons have been traveling ever since, stretched by the expansion of space into microwave wavelengths, and they fill the sky in every direction with a nearly uniform glow. Nearly uniform, but not perfectly. The CMB contains tiny fluctuations in temperature, slight variations of a few parts in 100,000, and the pattern of those fluctuations contains a staggering amount of information about the early universe. It is, in a sense, the oldest photograph we have, and buried within that photograph is evidence of something that existed before the thermal cosmos was born. The key lies in a feature called superhorizon fluctuations. To understand what these are, consider the concept of a cosmic horizon. In the time since the hot Big Bang, light has only been able to travel a finite distance. This sets a maximum scale over which different regions of the universe can have been in causal contact, meaning they could have exchanged information, equalized temperatures, or influenced each other in any way. Fluctuations on scales larger than this horizon should not exist, because there would have been no physical mechanism to create correlations between regions that have never communicated. And yet, the CMB shows correlations on precisely those superhorizon scales. The way this is detected is through a technique called TE cross-correlation, comparing the temperature fluctuations in the CMB with its E-mode polarization pattern on the same angular scales. Data from the WMAP satellite, first published in 2003, revealed these cross-correlations extending to scales well beyond the cosmic horizon. The Planck satellite confirmed and refined the result with even greater precision. In a universe that began with a singular hot Big Bang and nothing before it, these correlations should not be there. But in a universe that experienced a period of inflation before the hot Big Bang, a period during which quantum fluctuations on tiny scales were stretched to enormous sizes by the exponential expansion, these superhorizon correlations are exactly what you would expect. This is not an interpretation. It is a measurement. The fingerprints of inflation are embedded in the oldest light in the universe, written in the statistical relationships between temperature and polarization across the sky. And those fingerprints tell us, with the quiet authority of data, that something existed before the hot Big Bang. Something stretched space. Something seeded the cosmos with the patterns from which galaxies, stars, and eventually minds would emerge. The before is real, and we have already begun to read its signature. In 1981, Stephen Hawking stood before an audience at the Vatican, an institution built in part on the idea of creation, and proposed something that, depending on your perspective, was either profoundly modest or breathtakingly bold. He suggested that the universe might have no beginning at all, not that the beginning was unknowable, not that it was hidden behind some impenetrable barrier, but that it simply did not exist. That the question, what came before, was not difficult to answer but genuinely meaningless, like asking what is south of the South Pole. 2 years later, Hawking and the American physicist James Hartle published a paper that gave this idea a precise mathematical form. It became known as the no-boundary proposal, and its central image has become one of the most quietly astonishing in all of modern cosmology. Picture a shuttlecock, the feathered object used in badminton. It has a rounded bottom, a point at its base, and it widens smoothly as you move upward. In Hartle and Hawking's model, the universe has a shape like this in 4 dimensions. The wide open top represents the expanding cosmos we live in, space growing larger as time moves forward. But as you trace backward toward the origin, the universe does not narrow to a sharp point. It rounds off. It closes smoothly, like the surface of a sphere, so that there is no edge, no boundary, no moment at which you arrive at the beginning. The way this works mathematically involves a concept that is both elegant and deeply strange. Near the origin of the universe, the dimension we call time gradually becomes indistinguishable from a spatial dimension. Time does not stop or break, it smoothly transforms. And in a universe where time has become space near the origin, there is no before, in the same way that there is no direction north once you are standing at the North Pole. Hartle and Hawking derived a formula they called the wave function of the universe, a single mathematical expression that encompasses the entire history of the cosmos, past, present, and future, without requiring any initial conditions, any input, any cause. The universe in this picture does not need anything to start it. It is self-contained, complete, closed like the surface of a sphere, finite but without a boundary. This is a profoundly different answer to our question than anything that came before it. It does not say something existed before time. It says that before time is a phrase that refers to nothing, not because we lack information, but because the geometry of the universe makes the question structurally inapplicable. The beginning is not missing. It is simply not the kind of thing the universe has. Whether this is comforting or unsettling may depend on the listener, but its mathematical coherence is remarkable, and the debate it sparked, which continues to this day, has shaped every serious discussion of the origin of the cosmos for the past 4 decades. To make the no-boundary proposal work, to get the shuttlecock to round off smoothly instead of ending in a sharp singular point, Hawking needed a mathematical tool that sounds at first like something from a fever dream. He replaced real time with imaginary time, not imaginary in the everyday sense, not fictional or made up. Imaginary in the precise mathematical sense, time multiplied by the square root of -1. In mathematics, imaginary numbers are as rigorously defined and operationally useful as ordinary numbers. They show up everywhere, from electrical engineering to quantum mechanics, but their application to the origin of the universe carries a conceptual weight that goes far beyond technical convenience. Here is what imaginary time does. In the ordinary equations of general relativity, time and space behave differently. Time has a negative sign in the equations. Space has a positive sign. This difference is what makes time feel different from space. It is why you can turn around in space but not in time, why you can revisit a place but not a moment. When you replace time with imaginary time, that negative sign becomes positive, and suddenly, time behaves exactly like another dimension of space. In this imaginary time picture, the sharp point of the singularity, the moment of infinite density at the supposed beginning, smooths out. Instead of a cone with a singular tip, you get something more like the bottom of a bowl, rounded, continuous, no edge. The geometry near the origin becomes like the surface of a four-dimensional sphere, curving gently in every direction, including what used to be the time direction. This is the heart of the no-boundary proposal. In imaginary time, the universe is a closed, finite, four-dimensional surface with no boundary at all, and the transition back to real time, the time we experience, the time that clocks measure, happens gradually and smoothly as the universe expands and cools. There is no sharp moment at which time begins. There is only a gentle emergence, like the way the North Pole of a globe is a perfectly ordinary point on the surface, even though all lines of longitude converge there. Now this raises an obvious question. Is imaginary time real? The answer depends on what you mean by real. In quantum mechanics, imaginary numbers are not optional extras. They are woven into the basic structure of the theory. The wave function that describes every quantum system involves the square root of -1. Probabilities are calculated by taking the absolute square of complex amplitudes. The quantum world does not merely tolerate imaginary numbers, it requires them. Hawking argued that imaginary time might be equally fundamental to the description of the universe, that the question of whether imaginary time or real time is more real may not be a meaningful question at all. Both are mathematical descriptions, both yield predictions, and the predictions of the no-boundary proposal, calculated in imaginary time, describe a universe that is remarkably similar to the one we actually observe, smooth, expanding, and governed by the laws of physics without needing any external cause to set it in motion. There are physicists who disagree. Some have argued that the mathematical procedures Hawking used are ambiguous, that the path integral, the sum over all possible histories of the universe, can be performed in ways that give very different results. The debate is ongoing. But the image remains, a universe in which time, near the origin, gently ceases to be time and becomes something more like space. And in that transformation, the question of before dissolves, not because we cannot answer it, but because the geometry has carried it away. Alexander Vilenkin was working at Tufts University in 1982 when he proposed an idea so stark that many physicists initially did not know what to make of it. The universe, he suggested, came into existence by quantum tunneling from literally nothing, not from empty space, not from a vacuum fluctuation, not from some prior state or pre-existing condition. From nothing, no space, no time, no matter, no energy, no laws, no structure of any kind. In quantum mechanics, tunneling is a well-established phenomenon. A particle confronted with an energy barrier, a wall it does not have enough energy to climb over, can nevertheless appear on the other side. It does not go through the wall, it does not go over it. It simply has a non-zero probability of being found beyond the barrier, and nature, being quantum, occasionally realizes that probability. This happens constantly in the subatomic world. It is the mechanism behind radioactive decay, behind the nuclear reactions that power the sun, behind the operation of electronic components in the device on which you might be hearing these words. Vilenkin's radical step was to apply this logic to the entire universe. He proposed that the laws of quantum mechanics, or something like them, could apply even in the absence of space and time, that the state of absolute nothing was quantum mechanically unstable, that a tiny closed sphere of space-time could tunnel into existence from this state of nothingness, appearing with a small but non-zero probability, already equipped with the conditions needed to inflate and expand into a full cosmos. The mathematics of Vilenkin's tunneling proposal is related to, but distinct from, Hartle and Hawking's no-boundary model. Both use the tools of quantum cosmology, the application of quantum mechanics to the universe as a whole. Both involve path integrals and wave functions of the universe. But where Hawking's proposal eliminates the need for a beginning by smoothly rounding off time into space, Vilenkin's proposal keeps the beginning but transforms it. The universe does begin, but it begins from nothing, through a quantum event that requires no cause, no prior state, and no external trigger. This raises deep philosophical questions. Can something come from nothing? Does the word nothing even have a coherent meaning in physics? Vilenkin was careful to distinguish his nothing from the physicist's vacuum, which is actually a rich and dynamic entity filled with quantum fields and virtual particles. His nothing was emptier than empty. It was the absence of everything, including absence itself. And yet, quantum mechanics, or at least the mathematical structure that resembles quantum mechanics, still applied. The tunneling probability could still be calculated, the wave function of the universe could still be written down, and the resulting cosmos, emerging from this calculation, looked startlingly like the one we inhabit. Whether this constitutes a genuine explanation or merely pushes the question back one step further, what determined the quantum laws that allowed the tunneling, remains a matter of honest disagreement among physicists and philosophers. But the proposal itself stands as one of the most audacious in the history of cosmology. The idea that existence itself is a quantum fluctuation, and that the reason there is something rather than nothing is simply that nothing was never stable enough to last. Not every physicist was satisfied with proposals that eliminate the beginning entirely. Some took a different path, one that preserves time as continuous and unbroken, but replaces the singular origin with something gentler. A bounce. The idea emerges most naturally from loop quantum gravity, one of the leading candidates for a theory of quantum gravity. In loop quantum gravity, space is not a smooth, continuous fabric. At the smallest scales, the Planck scale, it is woven from discrete units, tiny loops of gravitational field that form a kind of atomic structure of space itself. These loops, or spin networks, are the fundamental building blocks from which geometry emerges, and they have a crucial property: they resist infinite compression. There is a minimum volume below which space simply cannot be squeezed. This single feature changes everything about the origin story. In classical general relativity, if you trace the expanding universe backward in time, the density increases without limit. Space contracts to a point. The curvature becomes infinite. The theory breaks. But in loop quantum gravity, as the density approaches a critical value, roughly the Planck density, the quantum structure of space generates a repulsive force, a force that grows stronger as compression increases, and that eventually becomes powerful enough to halt the collapse and reverse it. The singularity is replaced by a bounce. Martin Bojevold, working at Penn State University, was among the first to develop this idea in mathematical detail. Using the equations of loop quantum cosmology, he showed that the quantum evolution of the universe extends smoothly through the point where classical theory predicts a singularity. There is no breakdown, no infinite density, no edge of time. Instead, the equations describe a contracting universe, a previous cosmos, shrinking under its own gravity, that reaches maximum compression and then rebounds into expansion. Our expanding universe, in this picture, is the aftermath of a prior universe's collapse. Time, in the Big Bounce scenario, does not begin. It turns a corner, like a ball thrown against a wall that bounces back, except the ball is the entire fabric of space, and the wall is the quantum resistance of the smallest possible volumes. The implications are striking. If the bounce is real, then there was a universe before ours, a cosmos that existed, evolved, perhaps even contained its own structures and complexities, before contracting to a state of unimaginable density and re-expanding as the universe we now inhabit. The question what existed before time would have a startlingly concrete answer: more time, a previous epoch, a preceding chapter in a story that may have no first page. There are still open questions. Whether information survives the bounce, whether anything about the previous universe is preserved in the structure of the current one, remains debated. The equations suggest that some features carry through, while others are scrambled beyond recovery. The bounce acts as a kind of partial reset, wiping some of the cosmic slate clean, while leaving faint traces that, in principle, might be detectable. A universe that bounces is a universe that remembers, however faintly. And it is a universe in which the beginning is not a beginning at all, but a transition, a moment of maximum compression from which everything we know emerged. Some of the most striking proposals about the pre-bang cosmos do not come from modifying general relativity or quantizing gravity. They come from an entirely different direction, from the higher dimensional geometry of string theory, where our familiar universe is reimagined not as all there is, but as a surface floating in a much larger space. In string theory, the fundamental objects are not point particles but tiny, vibrating strings of energy, and for the mathematics of string theory to be consistent, the universe must contain more than the three spatial dimensions we experience. The extra dimensions are typically thought to be curled up at unimaginably small scales, hidden from direct observation. But in certain formulations, particularly in the 11-dimensional framework known as M-theory, our three-dimensional universe could be a membrane, or brane, embedded in a higher dimensional bulk space, and it might not be the only brane in that bulk. This is the starting point for the ekpurotic scenario, developed by Paul Steinhardt and Neil Turok in the early 2000s. The word ekpurotic comes from the ancient Greek concept of ekpurosis, the idea that the cosmos is periodically destroyed and reborn by fire. In Steinhardt and Turok's model, the fire is not literal. It is the collision of two branes. Picture two vast parallel membranes floating in a higher dimensional space, separated by a small gap. Each brane is a universe unto itself. Over immense stretches of time, these branes are drawn toward each other by a force analogous to gravity. They approach slowly, almost imperceptibly, and then they collide. The collision is not gentle. It converts the kinetic energy of the approaching branes into a flood of matter, radiation, and heat, precisely the conditions we associate with the hot Big Bang. In this picture, the Big Bang is not the beginning of time. Time existed before the collision, during the long approach of the two branes through the bulk. The universe before our Big Bang was a cold, nearly empty brane drifting toward its partner across a higher dimensional void. The collision was a transition, violent, transformative, but not a creation ex nihilo, more like two tectonic plates colliding and thrusting up a mountain range, except the mountain range is the entire observable universe. Steinhardt and Turok went further, proposing that this process is cyclic. After each collision, the branes pull apart. The universe on each brane expands and cools. Dark energy eventually dominates, and the expansion slows. The branes begin to approach each other again, drawn by the interbrane force, and eventually collide once more. Each collision is a new Big Bang. Each cycle produces a new thermal cosmos, and there is no first cycle. The process extends backward in time without limit. The ekpurotic model avoids the singularity not by quantizing space, as loop quantum gravity does, but by embedding our universe in a larger geometric context where the collision, however energetic, never produces a point of infinite density. The before in this scenario is not exotic. It is simply a previous phase of a larger cyclic process, a process in which universes are born, evolve, and set the stage for their own successors endlessly. There is another path through string theory's landscape that leads to a before, one that predates the ekpurotic scenario and emerges from a different aspect of string theory's mathematics. It was developed in the early 1990s by Gabriele Veneziano and Maurizio Gasparini, and it begins with a symmetry so fundamental to string theory that it cannot be discarded without dismantling the entire framework. In string theory, the equations that describe the universe possess a kind of time-reversal duality. For every solution that describes an expanding, decelerating cosmos, the kind of universe we observe today, there exists a mirror solution that describes a contracting, accelerating one. These two solutions are connected by the theory's own symmetry, and Veneziano and Gasparini realized that this mirror solution could describe a real, physical epoch that preceded the Big Bang. In their pre-Big Bang scenario, the universe did not begin in a hot, dense state. It began, or rather it has always existed, in a state that was cold, nearly flat, nearly empty, and expanding very slowly. Over time, under the influence of a scalar field called the dilaton, This cold, diffuse universe began to contract and heat up in certain regions. The dilaton, which is unique to string theory and determines the strength of all fundamental interactions, grew stronger and drove a phase of accelerating contraction, a kind of inflation in reverse, running backward in time. As the contraction intensified, the curvature of space increased, the temperature rose, the density climbed, and eventually the universe entered a regime of extremely high curvature, a stringy phase where the extended nature of strings becomes important and classical general relativity no longer applies. This high curvature phase is the bridge between the pre-Bang and post-Bang eras. On the far side of it, the universe transitions into the hot, expanding state we recognize as the standard hot Big Bang. What makes this scenario distinctive is its starting point. Unlike the Big Bounce, which begins with a collapsing universe of finite age, and unlike the ekpyrotic model, which begins with drifting branes in a higher dimensional space, the pre-Big Bang scenario begins from an almost trivial condition, a nearly flat, nearly empty, infinitely old universe in which almost nothing is happening. The drama arises not from some cosmic catastrophe, but from the slow, inevitable amplification of tiny perturbations by the dilaton field. The universe in this picture was always there. The Big Bang was not the start of its existence, but the culmination of an infinitely long process of self-excitation. There is something quietly elegant about this. The idea that the most dramatic event in cosmic history, the birth of the thermal universe, grew from the most unremarkable of beginnings. That an eternity of near-nothingness, a cosmos so cold and empty it barely qualified as existing, could slowly, through the mathematics of string theory, gather itself into the conditions for a bang. The pre-Big Bang scenario is not the leading model in cosmology today. It faces technical challenges, particularly in explaining how the transition through the high curvature phase occurs, but it remains a serious proposal, published in major journals, cited thousands of times, and offering a vision of before that is both radical and strangely peaceful, an infinite past of gentle emptiness, slowly awakening. Somewhere in the 1960s, two physicists, Bryce DeWitt and John Archibald Wheeler, attempted something that, in hindsight, might be one of the most unsettling achievements in the history of physics. They tried to write down the quantum mechanical equation for the entire universe, and the equation they produced, now known as the Wheeler-DeWitt equation, turned out to contain a feature so strange that its implications are still being debated more than half a century later. The equation has no time variable. This is not an oversight. It is not a simplification made for convenience or a placeholder waiting to be filled in by future research. The absence of time in the Wheeler-DeWitt equation is a direct mathematical consequence of combining the two deepest frameworks in physics, quantum mechanics and general relativity, into a single description of the cosmos. When you apply the rules of quantum mechanics to the gravitational field of the entire universe, the quantity that emerges, the wave function of the universe, does not evolve. It does not change, it simply is. To feel the weight of this, consider what it means. In ordinary quantum mechanics, the wave function of a particle changes over time. You can ask where the particle is likely to be found now, and where it will probably be found a second from now. Time is the backdrop against which quantum evolution unfolds, but the Wheeler-DeWitt equation describes a system that includes everything, all of space, all of matter, all of energy, and crucially, time itself. There is no external clock against which the universe can evolve, because the clock is part of the system being described. The result is an equation that describes a static, timeless quantum state, a cosmos without a heartbeat, a totality in which the notion of one moment following another does not appear in the fundamental mathematics. Change in this picture is not a feature of reality. It is something that emerges from within, a kind of internal correlation between different parts of the universal wave function, rather than an unfolding of events along a temporal axis. Physicists have struggled with this for decades. Some have argued that the Wheeler-DeWitt equation is telling us something profound, that time at the deepest level is an illusion, that the universe is a frozen four-dimensional block, and the experience of temporal flow is a feature of our perspective within it, not a feature of the block itself. Others argue that the absence of time is an artifact of the equation's limitations, a sign that the full theory of quantum gravity will restore time in some modified form. What cannot be denied is this. When physicists attempt to describe the universe at its most fundamental level, the description they arrive at does not include a clock. The cosmos, in its deepest mathematical representation, appears to exist all at once, beginning, middle, and end coexisting in a single, changeless structure. For the question of what existed before time, the Wheeler-DeWitt equation offers a response that is less an answer and more a dissolution. If time is not fundamental, if it does not appear in the master equation of reality, then before is not a direction you can travel in. It is a concept that belongs to the approximate, emergent description of the world, not to the world itself. And the search for what came before time becomes, in a sense, the search for something that the universe at its roots does not acknowledge. Julian Barbour has spent most of his career saying something that most people find almost impossible to accept. He says there is no such thing as time. Not that time is difficult to understand, not that time is relative or flexible or strange, but that it does not exist. That what we call time is a story we tell ourselves about patterns in a timeless reality, and that the story, however compelling, refers to nothing fundamental. Barbour is a British physicist who has worked largely outside the university system, independently pursuing questions about the foundations of physics for decades. His central idea, developed over years of careful thought, begins with a simple observation. When we say that time has passed, what we actually mean is that things have changed. A clock's hands have moved, the earth has rotated, neurons have fired. We never experience time directly. We only experience change, differences between configurations of the world. And Barbour asks, what if that is all there is? What if change is real, but time is not? He calls his framework Platonia, named loosely after Plato's realm of ideal forms. In Barbour's picture, every possible arrangement of every particle in the universe is a single point in an abstract, unimaginably vast space of configurations. Each point is a now, a complete instantaneous snapshot of everything, and reality, according to Barbour, is the collection of all these nows existing simultaneously, without any of them being arranged in a temporal sequence. There is no flow from one now to the next. There is no before and after. There are only configurations, frozen, complete, each one a self-contained world, and some of them contain internal structures that create the impression of time. A photograph that includes a clock, a blurred object in motion, a melting ice cube. These configurations carry within them the records that we interpret as evidence of a past and expectation of a future, but the records are part of the snapshot. The past they seem to recall does not need to have actually happened. The future they seem to anticipate does not need to actually arrive. This sounds radical. It is radical. But Barbour points out that it is not entirely without precedent. The Wheeler-DeWitt equation, as we just considered, already describes a timeless universe. Barbour's framework offers an interpretation of what that timelessness might look like. Not a frozen block of space-time, but a vast, unordered collection of possible worlds, each one complete, none of them happening in sequence. The implications for our question are striking. If Barbour is right, then asking what existed before time is like asking what is north of a map that has no north-south orientation. The question presupposes something, a temporal ordering, that reality simply does not possess. There is no before the beginning, because there is no sequence in which a beginning would be first. And yet we sit here, in what feels unmistakably like a flowing present, with memories of a past that feels real and a future that feels open. Barbour does not deny the richness of this experience. He simply suggests that it arises from the structure of individual nows, from the patterns within each frozen configuration, rather than from any actual movement through time. The river of time, in this view, is a painting of a river, detailed, convincing. But still, there is a coffee cup cooling on a desk somewhere as you listen to this. It was hot when it was poured. It is slightly less hot now, and by morning it will have reached the temperature of the room. This process, the slow equalization of temperature, The gentle drift from order to disorder is so ordinary, so unremarkable, that it barely registers as significant, but it may contain, hidden in its quiet unfolding, the deepest secret about the nature of time itself. Carlo Rovelli, an Italian theoretical physicist and one of the founders of loop quantum gravity, has spent years developing an idea that inverts the usual relationship between time and temperature. In the standard picture, time comes first. Events happen in time. Systems evolve in time. Temperature is a property of matter at a given moment in time. But Rovelli, building on earlier work with the mathematician Alain Connes, proposed something startling: that time does not come first, that time emerges from temperature, that the flow of time is not a fundamental feature of the universe but a consequence of our thermodynamic perspective on a deeper, timeless reality. This is the thermal time hypothesis, and its logic is subtle but surprisingly coherent. Start with a system in thermal equilibrium, a box of gas at uniform temperature, for example. In such a system, nothing changes macroscopically. There is no arrow pointing from past to future, no direction to time. The system just sits there, static, balanced. Now imagine you do not know the precise state of every particle in the box. You only know the macroscopic properties: temperature, pressure, volume. This ignorance, this statistical description, defines what physicists call a thermal state. Rovelli and Connes showed that every thermal state naturally generates a flow, a mathematical flow, not a physical one, but a flow that has exactly the properties we associate with time. It is one-dimensional, it is continuous. It moves from states of lower probability to states of higher probability. And when you apply this construction to the real universe, to the quantum state of the gravitational field, as described by the Wheeler-DeWitt equation, the thermal flow that emerges looks exactly like what we experience as the passage of time. The implication is extraordinary. Time in this framework is not a stage on which thermodynamics plays out. Time is what thermodynamics looks like from the inside. The arrow of time, the fact that we remember the past and not the future, that eggs break but do not unbreak, that coffee cools but does not spontaneously reheat, is not imposed on the universe from outside. It arises from the statistical relationship between an observer and the quantum state of everything. Temperature, in a beautiful inversion, becomes the speed of time. Where temperature is high, time flows quickly. Events unfold rapidly. Change is fast. Where temperature is low, time slows. And at absolute zero, time would stop entirely. The connection is not metaphorical. It is derived from the mathematics of quantum statistical mechanics and holds up under rigorous analysis. For our question, what existed before time, the thermal time hypothesis offers a response that is neither evasion nor answer. It suggests that before time is not a place or a state or an era. It is what the universe looks like when there is no observer to generate a thermal perspective. Time does not exist independently. It is born from the relationship between a system and the information available about it. And in the deepest description of reality, that relationship may not always hold. Near the very origin, something unusual was happening to the concept of information. Or rather, something unusual was not happening because there was, in a meaningful sense, no information at all. This idea requires careful handling. We are accustomed to thinking of the laws of physics as eternal and unchanging, written into the universe from the first instant, like a program loaded into a computer before it boots up. The speed of light, the charge of an electron, the gravitational constant. These seem like fixed features of reality, present from the beginning, governing everything that has ever happened or ever will. But consider the Planck epoch. At temperatures exceeding 10 to the 32nd degrees, the universe was so hot, so compressed, so turbulent with quantum fluctuations that the distinction between one particle and another, one force and another, one region of space and another, dissolved entirely. The computing capacity of a system, its ability to process, store, and differentiate information, depends on its physical complexity. And at the Planck scale, complexity was essentially zero. The physicist Seth Lloyd, among others, has explored the idea that the universe can be understood as a quantum computer, a system that processes information through physical interactions. In this framework, the total number of operations the universe has performed since the Big Bang can be calculated, and it is finite. Run the clock backward and the number decreases. At the Planck time, the universe had performed roughly one operation. Before that, the number drops below 1. The universe, in a computational sense, had not yet begun to think. This leads to a provocative possibility that the laws of physics were not fully defined at the origin, that they were only approximately specified, vague, incomplete, lacking the precision we associate with them today, and that as the universe expanded, cooled, and complexified, the laws themselves sharpened, crystallized, became the precise, reliable regularities that govern the cosmos we now observe. This is not as outlandish as it sounds. In certain approaches to quantum gravity, the fundamental constants are not truly constant. They are expectation values of quantum fields, averages that emerge from underlying dynamics, and that may have fluctuated wildly in the extreme conditions of the early universe. The fine structure constant, which determines the strength of electromagnetism, may not have been precisely 1/137 at the Planck time. It may have been approximately that, with fluctuations that gradually died down as the universe settled into its current vacuum state. If this is correct, then the universe did not begin by obeying a pre-existing set of rules. It began in a state so raw, so undifferentiated, that rules could not yet be formulated, and the emergence of law, the gradual crystallization of precise physical regularities from an initial state of quantum indeterminacy, was itself part of the process of cosmic evolution. The universe wrote its own operating system, and it did so while already running. For the question of what existed before time, this perspective adds a new dimension. Perhaps the before was not a place where different laws held, or where time flowed differently, or where alternative physics prevailed. Perhaps it was a state so poor in information that the very concept of a law, including the laws that govern time, had not yet emerged. A realm not of different rules, but of no rules at all, not the absence of a universe, but the absence of the precision needed to call anything a universe. Set the theories aside for a moment. Set the equations aside. Let go, briefly, of the competing models and the mathematical formalisms and the names of physicists who have spent their careers on these questions, and sit with something simpler, something that might, if approached gently, open a quiet door in the mind. What does it actually feel like to consider the possibility that before does not apply? We are creatures of sequence. Everything we have ever experienced has come in order. First this, then that. We cannot remember the future. We cannot influence the past. The entire structure of our consciousness is built on the assumption that time is a line, extending in both directions, and that the present is a point moving along it. To ask what came before is as natural to us as breathing. It is the grammar of our cognition, and so when a physicist says that the universe might have no beginning, that time might round off into space, or emerge from temperature, or simply not exist at the fundamental level, the mind resists. Not because the idea is illogical, but because it requires us to use a faculty we do not naturally possess, the ability to think without time. Consider a sphere. Its surface is finite. You can measure its area with precision, but it has no edge, no boundary, no point at which the surface stops and something else begins. You can walk in any direction on the surface of a sphere and never reach an end. It is bounded but boundaryless, finite but without a limit. Now try to imagine time as something like this. Not a line extending infinitely in both directions, and not a line that terminates at some earliest moment, but a dimension that curves back on itself or smoothly transforms into something else near the origin. A dimension that is finite. The universe has a finite age, but that has no first moment, no starting point, no edge at which time begins. The difficulty is not intellectual. You can follow the logic. You can nod at the analogy. The difficulty is experiential. Your brain was not built for this. Natural selection did not reward ancestors who could intuit the topology of space-time. It rewarded ancestors who could track the seasons, predict the movements of prey, remember where food was stored. Time, for the purposes of survival, is a straight line with a clear direction. Everything else is an abstraction, and yet here you are, at the edge of sleep, entertaining the abstraction, holding in your mind, however loosely, the idea that the question what came before might be similar to asking what is south of the South Pole, a question that is grammatically correct but geometrically meaningless. Not unanswerable, not mysterious in the dramatic sense, simply inapplicable. There is something strangely restful about this. Not the rest that comes from finding an answer, but the rest that comes from realizing that a question you have been carrying, perhaps unconsciously, perhaps for years, may not require an answer, that the weight of it was not the weight of an unsolved problem, but the weight of a misframed one, and that setting it down does not mean giving up. It means arriving at a clearing where the question dissolves on its own, like mist meeting sunlight, leaving behind only the quiet landscape it was obscuring. There is a symmetry in physics that has been tested with extraordinary precision and found to hold in every experiment ever conducted. It is called CPT symmetry, and it states that the laws of physics remain unchanged if you simultaneously reverse three things: the charges of all particles, their spatial orientations, and the direction of time. Swap matter for antimatter, flip the universe as if in a mirror, and run the clock backward. The equations do not notice the difference. Our universe, however, seems to violate this symmetry in a very particular way. We live in a cosmos dominated by matter, not antimatter. Time flows in one direction, space has a definite handedness in certain particle interactions. The symmetry that the fundamental laws preserve, the actual state of the universe, appears to break. In 2018, three physicists, Latham Boyle, Kieran Finn, and Neil Turok, proposed a striking resolution. What if the universe does not violate CPT symmetry at all? What if the missing antimatter, the missing reverse time, the missing mirror image are not absent but simply on the other side of the Big Bang? Their model, called the CPT symmetric universe, proposes that the Big Bang is not a beginning but a mirror. On our side, time moves forward, matter dominates, space has its familiar orientation. On the other side, extending backward from the Big Bang, time moves in the opposite direction, antimatter dominates, and spatial handedness is reversed. The two halves together form a single CPT symmetric whole. Neither half is more real than the other. Neither came first. The Big Bang is the axis of symmetry between them. This is a universe in which asking what came before the Big Bang has a concrete physical answer: the anti-universe. A cosmos made of antimatter, evolving backward in time, structurally identical to ours but inverted in every respect that CPT symmetry demands. The model has consequences that can be tested. It predicts that dark matter, the invisible substance that makes up roughly a quarter of the universe's energy content, could consist of a particular type of neutrino called a sterile right-handed neutrino. These particles would have been produced naturally by the symmetry conditions at the Big Bang, without requiring any additional mechanism. If such neutrinos are detected, it would be strong evidence for the CPT symmetric picture. The model also predicts the absence of something. In standard inflationary cosmology, the rapid expansion of the early universe should have generated a background of primordial gravitational waves, ripples in spacetime that would leave a distinctive imprint on the polarization of the cosmic microwave background. The CPT symmetric model does not include inflation. It does not need it, and therefore it predicts that this gravitational wave signal should not be found. Astronomers are currently searching for exactly this signal, and the outcome of their search could distinguish between competing visions of the pre-bang cosmos. What makes this proposal quietly compelling is its economy. It does not add new dimensions, new fields, or new particles beyond what the standard model already contains. It simply takes the symmetry that the laws of physics demand and insists that the universe actually obey it, as a whole, across the entirety of its history, including the history that lies on the other side of the mirror. Roger Penrose has always been willing to follow a mathematical idea wherever it leads. even when it leads to places that make other physicists uncomfortable. His conformal cyclic cosmology is one such place, a vision of the universe's past and future that is at once simple in its logic and staggering in its implications. The starting point is an observation about the far future. If the current acceleration of the universe's expansion continues, driven by dark energy, then eventually all matter will be pulled apart. Galaxies will drift beyond each other's horizons. Stars will burn out. Black holes, the last massive objects, will slowly evaporate through Hawking radiation over timescales that dwarf the current age of the universe. And in the final state, all that will remain is a thin bath of photons and gravitons, massless particles traveling at the speed of light through an incomprehensibly vast, cold, empty space. Now here is Penrose's insight. For a massless particle, traveling at the speed of light, there is no experience of time. Photons do not age. They do not have clocks. The concept of duration is meaningless to them. And in a universe populated entirely by massless particles, the distinction between an enormous universe and a tiny one becomes, in a precise mathematical sense, irrelevant. Conformal geometry, the branch of mathematics that preserves angles but not distances, cannot tell the difference. Penrose proposed that this final state of the universe, when all mass has been radiated away and only massless particles remain, is conformally identical to the conditions just after a Big Bang. The exhausted end of one cosmic era, which Penrose calls an aeon, smoothly becomes the compact, energetic beginning of the next. No bounce, no collision, no tunneling, simply a mathematical reshaping, a conformal rescaling, in which the infinite future of one aeon becomes the point-like origin of the next. In this picture, the universe does not end, it forgets. As mass disappears and the concept of distance becomes meaningless, the universe loses its sense of scale, and in losing scale, it loses the ability to distinguish between being very old and very young. The slate is wiped not by destruction but by a kind of cosmic amnesia, and from that amnesia, a new aeon is born. Penrose has proposed that this process might leave traces, faint signals from the previous aeon, that survive the conformal transition and appear in the cosmic microwave background of the current aeon. He calls them Hawking points, tiny, anomalously warm spots in the CMB that could be the remnant signatures of supermassive black holes that evaporated in the aeon before ours. Their Hawking radiation, squeezed through the conformal boundary, would appear as concentrated points of excess temperature. Whether these Hawking points have actually been detected is a matter of active dispute. Penrose and collaborators have published analyses claiming to find them in the Planck satellite data. Other researchers have argued that the claimed signals are consistent with statistical noise. The question remains open, which is itself part of the fascination, but the image endures. A universe that does not stop. A cosmos that cycles through aeons, each one unimaginably long, each one forgetting everything about its predecessor except, perhaps, a few faint warm spots in the sky, the ghosts of black holes that lived and died in a previous version of eternity. Consider the mess in any room you have ever lived in. Books migrate from shelves to tables, clothes drift from drawers to chairs, dust accumulates. Entropy, the physicists' measure of disorder, increases steadily, quietly, inevitably. This is the second law of thermodynamics, and it is one of the most fundamental and least controversial principles in all of science. Disorder grows. Systems move from less probable states to more probable ones. The universe overall is running down. Now run this backward. If the universe is becoming more disordered over time, then the earlier you go, the more ordered it must have been. And if you follow this logic all the way to the beginning, to the hot Big Bang itself, you arrive at a state of almost inconceivable orderliness, a state so precisely arranged, so exquisitely structured, that its probability is nearly zero. Roger Penrose attempted to calculate just how improbable this initial state was. He estimated the number of possible configurations the universe could have started in, a measure of the total phase space available at the origin, and compared it to the specific configuration that would give rise to a smooth, uniform, low-entropy beginning like the one we actually observe. The result was a number so extreme that it defies ordinary comprehension: 1 in 10 to the power of 10 to the power of 123. That is not 10 to the 123. It is 10 raised to the power of 10 raised to the power of 123, a number with more digits than there are particles in the observable universe, more digits than any number that has ever been written down for any purpose in the history of mathematics. This is the low-entropy puzzle. The universe began in a state of extraordinary order, and no theory currently explains why. Inflation, which explains so much else about the early universe, does not solve this problem. Inflation takes whatever initial conditions it is given and stretches them, smooths them, flattens them, but it requires those initial conditions to already be moderately smooth and uniform for inflation to begin in the first place. It does not explain the orderliness, it presupposes it. This has led some physicists to suspect that the answer lies not in the dynamics of the early universe, but in the boundary conditions, in whatever selected the universe's initial state from the astronomically vast space of possible states. And this brings us back to the question of what existed before time, because if the initial conditions were not random, if they were selected by some principle, some law, some structural requirement, then whatever did the selecting must, in some sense, precede the Big Bang, not necessarily in time, perhaps in logic, perhaps in mathematics, perhaps in some framework we do not yet have a name for. The orderliness of the beginning is a clue, a fingerprint left by something we do not yet understand, something that shaped the before into an arrangement of almost impossible precision, and then allowed the second law of thermodynamics to carry it forward into the rich, complex, gradually disordering cosmos we inhabit tonight. The question is not only what existed before time, it is why the beginning was so improbably perfect. In 1986, the physicist André Linde realized something unsettling about the inflationary model he had helped develop. Inflation, once started, might never fully stop. The mechanism is rooted in quantum uncertainty. During inflation, the inflaton field, the energy field driving the exponential expansion, is subject to quantum fluctuations. In most regions, the field decays smoothly, ending inflation and releasing energy as the hot Big Bang. But in some regions, the fluctuations push the field upward rather than downward, preventing the decay and sustaining inflation a little longer. And because inflating space is expanding exponentially, these still inflating regions grow faster than the decaying regions shrink. The result is a process that feeds itself, inflation producing more space sustaining more inflation endlessly. This is eternal inflation, and its implications reshape the entire question of what came before. In this framework, our observable universe is not the universe. It is a pocket, a bubble that nucleated within a vast, still inflating background. When the inflaton field in our region happened to decay, other pockets are forming constantly, far beyond our cosmic horizon, each one experiencing its own hot Big Bang, each one potentially governed by different physical constants, different particle masses, different forces. The inflating background, the eternal self-reproducing foam, extends backward in time, and while some theorems suggest it cannot extend infinitely far into the past, others challenge even this conclusion. If eternal inflation is correct, then before our Big Bang was simply more inflation, and before that, more still. Our universe is one bloom in an infinite garden, and the garden has been flowering for an unimaginably long time, possibly forever. String theory adds another layer to this picture. The equations of string theory admit an enormous number of possible solutions, different ways the extra dimensions can be curled up, different values the fundamental constants can take, different configurations of the fields that fill space. The number of these possible solutions is estimated at roughly 10 to the 500th power. Each solution corresponds to a different possible universe, with different physics, different chemistry, different possibilities for complexity and life. The collection of all these possible solutions is called the string landscape. And if eternal inflation is populating the landscape, If each pocket universe that nucleates corresponds to a different point in this vast space of possibilities, then the answer to what existed before time is not a single state or a single event, but an infinite, branching, self-reproducing process that has been exploring the space of possible universes for longer than any clock could measure. This is simultaneously the most expansive and the most humbling answer to our question. It places our universe, everything we have ever known or could ever observe, as one bubble in an infinite foam, one flower in an endless garden, one experiment among 10 to the 500th power possible experiments. And it suggests that the before is not a mystery waiting to be solved, but a process so vast, so fertile, so relentlessly creative that our universe is just one of its countless quiet outcomes. Whether this vision is ultimately confirmed or replaced by something simpler remains to be seen, but its scope is worth sitting with, an infinity of universes generated by a process that may have no beginning, each one real, each one complete, each one unaware of the others. We have now travelled through 6 serious, mathematically grounded, physically motivated answers to the question of what existed before time. A universe without a beginning, a quantum tunnel from nothing, a bounce from a prior contraction, a collision of membranes in a higher dimensional space, a slow awakening driven by the dilaton of string theory, a mirror universe extending backward in antimatter, an eternally inflating foam, cycles of aeons connected by conformal rescaling, a timeless reality from which our experience of time emerges as a kind of thermodynamic perspective. These are not fringe ideas. They are not science fiction. They are published in the most respected journals in physics, debated at the most prestigious conferences, pursued by some of the most accomplished living scientists, and they contradict each other. The no-boundary proposal says there is no before. The Big Bounce says before was a contraction. Eternal inflation says before was more inflation. The CPT symmetric model says before was the anti-universe. Penrose says before was the dying aeon of a previous cosmos. Vilenkin says before was nothing at all. Not empty space, not vacuum, but the genuine absence of everything. It is tempting to feel frustrated by this, to want someone to choose to declare a winner, to resolve the multiplicity into a single clean narrative. But this impulse, natural as it is, may itself be a misunderstanding of how science works at its frontier. The frontier is not a line. It is not a sharp boundary between the known and the unknown. It is more like a fog, a region where visibility decreases gradually, where multiple paths seem plausible, where the landmarks are mathematical rather than observational, and where honest, competent explorers can disagree without either being wrong. The disagreement is not a failure of science. It is the signature of a question that is genuinely hard and genuinely open, and there is something important in this openness. The fact that multiple serious answers exist tells us that the question itself is well posed. It is not meaningless. It is not outside the reach of physics. It is not, as some have argued, a question that science cannot in principle address. The theories we have explored tonight are not guesses. They are frameworks, each with its own internal logic, each making its own predictions, each waiting to be tested against data that may arrive in the coming decades. Gravitational wave detectors may find or fail to find the signatures of inflation, constraining some models and supporting others. Neutrino experiments may or may not discover the sterile neutrinos predicted by the CPT symmetric model. CMB analyses may or may not confirm the Hawking points predicted by conformal cyclic cosmology. The future is an arbiter, and it has not yet spoken. In the meantime, what we have is not confusion but richness, a landscape of possibilities, each one beautiful in its own way, each one revealing a different aspect of the universe's capacity for self-explanation. The silence between these theories is not the silence of ignorance. It is the silence of a question still resonating, a question that the universe has heard but not yet fully answered. And there is a kind of peace in that. Not the peace of resolution, but the peace of knowing that the question is alive, that minds are working on it, that the universe is yielding its secrets slowly, patiently, To those who ask carefully, a peace that does not require certainty to be real. There are two ways to picture time, and they pull in opposite directions. The first is the way you experience it right now. Time is a river, flowing continuously from the past through the present and into the future. You are carried along on its current. The past recedes behind you. The future opens ahead. This moment, the sound of these words, the feeling of your body settling into stillness, is the leading edge of something in constant motion. The second is the way physics describes it. In Einstein's general relativity, time is not a river, it is a landscape. Past, present, and future coexist in a single, four-dimensional structure called space-time. Events do not happen one after another in any fundamental sense. They simply are, arranged in a geometric pattern, related to each other by distances and angles, but not flowing, not moving, not becoming. Physicists call this the block universe, and it is not a marginal or controversial idea. It is the direct consequence of the equations that have successfully described gravity, motion, and the large-scale structure of the cosmos for over a century. In the block universe, asking what came before the Big Bang is not a temporal question, it is a geometric one. You are not asking what happened earlier in a sequence of events. You are asking about the shape of the block near its boundary, whether it has an edge, whether it tapers to a point, whether it rounds off smoothly or connects to another block entirely. This is a subtle but important shift. When we ask about the before in everyday language, we imagine stepping backward along the river, moving upstream against the current, searching for the source. But in the block picture, there is no current. There is no upstream. There is only structure. And the question becomes, what is the geometry of reality near the point we call the Big Bang? Every model we have explored tonight offers a different answer to this geometric question. The no-boundary proposal says the block smoothly rounds off. The Big Bounce says it connects to a mirror image block through a narrow bridge. Eternal inflation says it extends indefinitely in the direction we loosely call backward. The CPT symmetric model says it is symmetric about a central point. And the Wheeler-DeWitt equation suggests that the block, at the deepest level, does not have a time direction at all. The tension between the river and the block, between how time feels and how it is described, runs through every question about the origin. We cannot help but frame the search in temporal language, because temporal language is all we have, yet the answers we receive are increasingly geometric, structural, mathematical. They do not speak of before and after. They speak of shape, topology, boundary conditions, and symmetry. Perhaps this is the deepest lesson so far. The question of what existed before time may not be answerable in the language of time. It may require us to think in a language we are still learning, a language of form rather than flow, of architecture rather than narrative. And the discomfort we feel in the gap between these two ways of thinking is not a problem to be solved. It is the authentic texture of a mind built by time, reaching for something beyond it. In the 5th century, Augustine of Hippo sat down to consider the question of time and arrived at a confession that still resonates. "What, then, is time?" he wrote. "If no one asks me, I know. If I wish to explain it to one who asks, I do not know." 16 centuries later, the question has not gotten easier. It has, in many ways, gotten harder. Because now we have theories that tell us time may not exist at the fundamental level, and we still do not have the language to say what that means. Language is not a neutral tool. It shapes thought. Every sentence you construct about time is built on assumptions that may not hold at the deepest level of reality. The word before presupposes a timeline, a sequence of moments arranged in order, extending backward. The word existed presupposes a present tense framework, a vantage point from which to assess what was real at some earlier time. Even the word what implies a thing, an entity, a something that occupied a prior position in a temporal sequence. Ludwig Wittgenstein argued that many philosophical problems are not genuine problems at all, but confusions arising from the misuse of language. The question what came before time may be one of these. Not because it is trivial, but because the grammar of the question imports assumptions that the answer may need to reject. And yet, and this is what makes the story of modern cosmology so remarkable, physicists have found ways to give precise mathematical answers to a question that the grammar of ordinary language renders almost incoherent. They have done this by replacing words with equations, by replacing before with boundary conditions, by replacing what existed with wave functions and path integrals and conformal rescalings. They have translated the question out of natural language and into mathematics. And in that translation, the question has not only survived but become tractable. This is a profoundly human achievement, not the achievement of any single physicist, but of the entire enterprise of mathematical physics, the centuries-long project of learning to describe reality in a language more precise than the one evolution gave us. A language in which before time does not generate a paradox but a research program. A language in which nothing can be given a technical definition and a probability. A language in which the absence of a boundary can be stated as a positive condition, not a mystifying gap. The gap between our grammar and our mathematics is not a flaw. It is a record of how far we have traveled. We began as creatures who could barely articulate the question. We became creatures who could formalize it. And now we are creatures who have multiple, competing, mathematically rigorous answers, even as we struggle to say, in plain words, what those answers mean. There is a kind of tenderness in this struggle, a species trapped in temporal grammar, reaching toward truths that grammar cannot hold, building, word by word and equation by equation, a bridge between the language of experience and the language of reality, never quite arriving, always getting closer. You are a time machine, not in the science fiction sense, not a device that travels to other eras, but in the deepest biological sense. Every structure in your brain was selected over hundreds of millions of years of evolution for its ability to process temporal information, to track cause and effect, to store the past as memory, to model the future as anticipation, to experience the present as a fleeting, urgent now that demands attention and response. Your neurons fire in sequences, your synapses strengthen through repetition over time. Your hippocampus encodes events by their temporal order: what happened first, what happened next, what happened last. Even your perception of a single moment is, in truth, a construction assembled from sensory inputs that arrive at slightly different times and are stitched together by your brain into the seamless experience of right now. Time is not something you observe from outside. It is the medium in which your consciousness operates. It is the scaffolding on which every thought, every feeling, every experience is built. Without temporal processing, there is no memory, no anticipation, no sense of self, no narrative, no meaning. You are, in a very literal sense, made of time, and here you are, at the boundary of sleep, trying to think about its absence. This is a poignant situation. A creature whose every cognitive faculty depends on temporal ordering is attempting to genuinely comprehend a state in which temporal ordering does not apply. It is like a fish trying to understand dryness. Not impossible, abstraction is powerful, but inherently limited in a way that cannot be fully overcome. When you try to imagine the no-boundary proposal, you cannot help but picture it as a sequence. First there was the rounded bottom of the shuttlecock. Then the universe expanded upward, but the whole point of the proposal is that there is no first. When you try to imagine the Wheeler-DeWitt equation's timeless cosmos, you picture a frozen block, but your picture has a viewer standing outside the block, looking at it from a temporal perspective that the equation denies. Every metaphor we use for timelessness smuggles time back in through the back door. We say the universe simply is, but is a present tense verb, implying a moment of being. We say all moments coexist, but coexist implies a shared now. Our language is not merely inconvenient, it is structurally inadequate for the task. This is not a reason for despair. It is a reason for humility. The physicists who work on these questions know they are operating at the edge of what human cognition can comfortably handle. They use mathematics precisely because mathematics can express relationships that language and intuition cannot. The equations do not need to be pictured, They work whether or not we can visualize what they describe. And so, tonight, as your mind softens and the grip of waking thought begins to loosen, consider this. The inability to fully imagine timelessness is not a failure. It is a feature of being the kind of creature you are. A creature born inside time, shaped by time, sustained by time. And the fact that such a creature can even formulate the question, can even build the mathematics that approaches an answer, is itself something quietly extraordinary. Physicists have answers. This deserves to be said plainly, because it is easy to lose in the haze of competing models and open questions. The title of this journey promised answers, and we have encountered them, not one, but many, each supported by serious mathematics, each grounded in decades of theoretical work, each making predictions that can in principle be tested. The no-boundary proposal says the universe has no beginning, because time becomes space near the origin. The Big Bounce says a contracting universe preceded ours and rebounded at maximum density. The CPT symmetric model says an anti-universe extends backward from the Big Bang in mirror image. Penrose's conformal cyclic cosmology says our universe emerged from the exhausted remnants of a previous aeon. Vilenkin's tunneling proposal says the universe appeared from nothing via a quantum event. Eternal inflation says our cosmos is one pocket in an endlessly self-reproducing foam. And the Wheeler-DeWitt equation, in its austere way, says that time was never fundamental to begin with. These are not speculations in the loose, everyday sense. They are structured, mathematically coherent frameworks, published in peer-reviewed journals, refined over years, and debated with precision. They represent the best attempts by some of the most capable minds in human history to answer a question that, a century ago, was considered beyond the reach of science entirely. The fact that there is not yet a single, agreed-upon answer is not a failure. It is the honest shape of a science still in motion. The tools that will eventually distinguish between these models are currently being built, refined and deployed. Gravitational wave observatories, both on Earth and planned for space, are approaching the sensitivity needed to detect or rule out primordial gravitational waves, the presence or absence of which would constrain inflationary models and support or challenge alternatives like the CPT symmetric proposal. Neutrino experiments are probing the properties of the lightest and most elusive particles in nature, searching for the sterile neutrinos that some models predict and others do not. CMB observations continue to improve in resolution and precision, offering the possibility of detecting the faint anomalies, like Penrose's Hawking points, that would provide evidence for cyclic cosmology. The incompleteness of our knowledge is not a void, it is a frontier. And frontiers are not places where science has failed. They are places where science is most alive, where the next measurement, the next calculation, the next theoretical insight could shift the landscape dramatically. Every model we have discussed tonight is an invitation, not a conclusion, an opening, not a closing, a beginning, not an end. And perhaps there is something valuable in receiving answers that are multiple rather than singular. A single answer closes a question. Multiple answers keep it breathing. They remind us that the universe is complex enough, deep enough, and strange enough to accommodate more than one coherent origin story within its own mathematics. The plurality is not a problem. It is a reflection of the depth of the question itself. Consider what it means that this question remains open. Not open in the sense of abandoned or neglected, open in the sense of alive, vibrating, still yielding surprises, still attracting brilliant minds, still connecting to observations that are being gathered right now, tonight, by instruments circling the Earth and scanning the sky. The question of what existed before time is not a relic of armchair philosophy. It is one of the most active research areas in theoretical physics and observational cosmology. Papers are being published this year that refine, challenge, and extend the models we have explored. Graduate students are beginning careers devoted to these questions. Telescopes are being designed specifically to test predictions that emerge from pre-bang theories. The question is not settling into a comfortable retirement. It is intensifying, and here, at the edge of the inquiry, something unexpected happens. The question itself begins to feel less like a problem and more like a landscape, a space you can inhabit without needing to conquer. The competing models are not warring factions demanding your allegiance. They are perspectives, different vantage points from which to view the same vast, half-hidden territory. And the territory is real. Whatever existed before time, whether it was nothing or everything or a mirror or a bounce or an infinite garden of inflating space, it is not waiting for human consensus to be what it is. It simply is what it is, patient and complete, indifferent to our debates, holding its shape whether or not we ever fully understand it. There is a kind of beauty in this patience, a kind of grace in the universe's willingness to remain partially opaque. We live in a cosmos that answers enough questions to keep us engaged, but retains enough mystery to keep us humble. It gives us the cosmic microwave background, that ancient light carrying the signatures of its earliest moments. It gives us the mathematics of quantum mechanics and general relativity, powerful enough to reach back to within a fraction of a second of the origin. And then it draws a gentle curtain, the Planck curtain, and invites us to imagine what lies behind it, without yet confirming which imagination is correct. Perhaps what existed before time was not a thing at all, not a state, not a condition, not an epoch. Perhaps it was a possibility, a mathematical structure that contained, within its logic, the potential for time, for space, for matter, for complexity, for minds that would one day lie in darkened rooms and wonder about their own origins. A seed that was not planted in time because time had not yet emerged, but that nevertheless gave rise to everything temporal, every second, every season, every life. Or perhaps it was something else entirely, something that our current theories only approximate, something that the next generation of physicists will describe in a language we cannot yet speak. The openness of the question is not a gap in our understanding. It is the growing edge of understanding itself, the place where knowledge is actively being made, where the unknown is not empty but fertile, not frightening but inviting. Tonight, as your thoughts begin to soften, let this be enough, that the question exists, that the answers are beautiful, and that the space between them is not darkness but a kind of light we have not yet learned to see. We have travelled a long way tonight, not in miles or in years, but in the kind of distance that only thought can cover. From the familiar ticking of clocks to the place where clocks dissolve, from the ordinary understanding of beginnings to a frontier where beginning loses its meaning entirely. Along the way, certain images have gathered. The Planck curtain, that veil at 10 to the negative 43 seconds, where the universe's own structure prevents us from seeing further with the tools we currently possess. The shuttlecock of Hartle and Hawking, rounding smoothly at its base, closing off the question of before with the quiet geometry of a sphere. Vilenkin's tunnel, an entire cosmos flickering into existence from a nothing so absolute that even emptiness would be too much to call it. The Big Bounce, where time does not begin but bends, where a contracting universe folds through maximum density and unfolds again as hours. The Brane collision, two vast membranes meeting in a higher dimensional space, their impact lighting the universe like a match struck in an infinite room. The slow, cold awakening of string cosmology, where a nearly empty cosmos gradually heated itself over an eternity of near stillness. The anti-universe, extending backward from the Big Bang in antimatter and reverse time, completing a symmetry that the laws of physics insist upon. The aeons of Penrose, cycling endlessly, each one forgetting everything about its predecessor except a few warm ghosts in the microwave sky. The improbable orderliness of the beginning, a precision so extreme it dwarfs every number ever written. The garden of eternal inflation, blooming with pocket universes beyond counting. And underneath it all, the deeper suggestions that time may not be fundamental, that the master equation of the universe contains no clock, that what we experience as the flow of moments may be a story told by thermodynamics, a narrative woven by heat and entropy from a reality that, at its roots, is still. These are not conclusions, they are companions for the quiet hours, ideas to hold loosely, the way one holds a smooth stone found at the edge of the sea, not for any purpose, but for the way it fits in the palm. Let them settle now. They do not need to be ranked or resolved. Each one is a window, and through each window the view is different, and all of them are real. If time is not fundamental, if it emerges from deeper structures, from thermodynamic flows, from the internal logic of frozen configurations, then something extraordinary follows about the fact that you are here, aware, listening to these words in what feels, unmistakably, like a flowing present. You are a pattern in the universe that experiences time, not because the universe requires time to exist, but because the particular arrangement of matter and energy that constitutes your body and your brain generates, from within, the sensation of temporal flow. You are the cosmos dreaming that it has a past and a future. You are the block universe catching a glimpse of itself from the inside and interpreting what it sees as movement, as sequence, as the passage of one moment into the next. This is not a diminishment, it is an elevation. If time is emergent, then consciousness, your consciousness, this very awareness, is among the most remarkable phenomena in existence. It is the universe creating, from its own timeless fabric, the experience of time. It is the mathematical structure generating a perspective. It is the equation producing a reader. Right now, the atoms in your body are the same atoms that were forged in the hearts of stars billions of years ago. The carbon in your bones, the iron in your blood, the oxygen filling your lungs, all of it was cooked in stellar furnaces and scattered across space by supernovae long before the Earth existed. You are assembled from the debris of ancient explosions, organized by billions of years of chemistry and evolution into a form that can lie in a darkened room and contemplate the origin of time. And if the models we have explored tonight are even approximately correct, then the story goes deeper still. The quantum fluctuations that seeded the large-scale structure of the universe, the slight density variations that grew into galaxies and clusters, were stretched from the quantum vacuum by inflation, which itself may have been preceded by a bounce, or a tunneling event, or a conformal transition, or an infinite process of eternal self-reproduction. The chain of causation that leads to this moment, your awareness, your gentle breathing in the dark, extends back through the hot Big Bang, through inflation, through whatever preceded inflation, perhaps through the Planck epoch, perhaps through a previous universe, perhaps through nothing at all. And at some point along that chain, the concept of chain itself breaks down, because the links are no longer temporal, they are logical, mathematical, geometric. You are connected to the origin, not metaphorically, physically. Every particle in your body carries the signature of processes that occurred at the edge of time, and your awareness of this connection, your ability to think about it, to wonder about it, to feel something in response to it, is itself part of the universe's unfolding. Whatever existed before time, it eventually became you. There is a kind of rest that does not come from answers. It comes from something quieter, from the willingness to hold a question without needing to resolve it, from the recognition that not knowing is not the same as ignorance, and that the space between a question and its answer can be a place of peace rather than anxiety. The physicists who work on these questions, the ones who spend their days with the Wheeler-DeWitt equation, with path integrals and conformal rescalings and the boundary conditions of the cosmos, they do not seem tormented by the lack of a final answer. They are engaged, they are curious, they are by all accounts remarkably calm in the presence of the unsolved. They treat the open question not as a wound but as a landscape, something to be explored, mapped, appreciated, without needing to be conquered. This calm is not indifference. It is the deep composure of someone who has learned to be comfortable with uncertainty, who has discovered that the work itself, the careful reasoning, the elegant mathematics, the slow accumulation of insight, is rewarding regardless of whether the final answer arrives in their lifetime. The journey is the point. The question well asked is its own gift. And this composure is available to anyone. You do not need to be a physicist to practice it. You do not need to understand the equations to benefit from their lesson. The lesson is simple. Some questions are too large to answer quickly, and the pressure to answer them immediately is not a requirement of the universe. It is a habit of the mind, A habit that can be gently released, the way a hand releases a held breath, the way a body releases tension it did not realize it was carrying. Tonight, you do not need to decide what existed before time. You do not need to choose between the bounce and the tunnel, between the mirror and the cycle, between timelessness and eternity. You are allowed to hold all of them. You are allowed to hold none of them. You are allowed to simply notice that the question exists, that it is beautiful, and that the universe is patient enough to hold it open for as long as it takes. The deepest rest comes not from certainty, but from the willingness to let go of the need for it. From the trust that the question is being held by the universe, by the community of minds working on it, by the slow, steady process of science, and that your job tonight is not to solve anything. Your job tonight is to rest, to let the thinking dissolve, to let the ideas drift, to let the questions settle into the same deep quiet from which, perhaps, everything once emerged. The room is still now. The ideas have run their course, like rivers finding the sea, and what remains is a kind of spaciousness, not empty, not void, but open, wide, unhurried. Everything we have explored tonight, the theories, the equations, the names, the numbers, has arrived at the same shore, the shore where knowledge meets the unknown and finds not a wall, but a horizon, a place where the edge of understanding is not sharp but soft, like the edge of sleep, like the boundary between waking and dreaming, where one state gently becomes the other without a clear dividing line. The universe may have no beginning. It may have emerged from nothing. It may be one in an infinite garden of possibilities, or one side of a perfect mirror, or one aeon in a chain of aeons, or a pattern in a timeless mathematical structure that does not need a first moment to be complete. Each of these answers carries its own beauty. Each one reshapes the landscape of the possible, and none of them asks anything of you tonight. Whatever was before time, if before even applies, it is not something you need to reach. It is not something you need to hold. It is already here, woven into the fabric of the present moment, encoded in the particles that make up your body, expressed in the silence between your thoughts. The origin is not far away. It is the deepest layer of the ordinary, the first draft of everything you have ever touched. The expansion of the universe continues. Right now, as your breathing slows, as your muscles release, as the day's accumulated weight lifts and dissipates, the space between distant galaxies is growing. Gently, imperceptibly, the cosmos is stretching, thinning, cooling, moving, as it always has, in the direction of greater stillness. And if Penrose is right, then at the end of that process, after unimaginable eons, the universe will reach a state of perfect calm, a state so still, so undifferentiated, so free of mass and structure, that it becomes indistinguishable from a beginning, stillness becoming creation, ending becoming origin, the old becoming the new, without anything needing to happen in between. And here, in this room, in this moment, you are part of that story, a point of awareness in the long arc between whatever came before and whatever comes after, a mind that has spent the last hours contemplating the deepest question a mind can ask, and now gently returns to the simplest thing a mind can do, rest. The unknown is not empty. It is the substance from which everything was made, and it is holding you now the same way it held the universe before the universe knew it existed. There is nothing more to reach for, nothing more to solve, only this, only quiet, only the gentle, infinite dark from which all light, eventually, is born.